You know, we often think of cancer as this single battle, right? A tumor growing in one spot. But the real, terrifying war, that begins when it starts to travel. Today, we're going to crack open cancer's secret survival guide. We're looking at this incredible discovery that shows exactly how melanoma cheats death during its most dangerous journey, the one right through our lymph nodes.
So let's just start with the most fundamental question there is. How does cancer actually become so deadly? Because, and this might surprise you, it's not usually the first tumor that poses the biggest threat.
The real danger, the thing that makes cancer so feared, is a process called metastasis. This is where those cancer cells break away, go on a journey through the body, and start setting up new tumors all over the place. And yeah, this spread, this is the #1 reason cancer is so fatal.
So let's talk about that journey. To really get how amazing this new research is, you first have to understand just how incredibly hard it should be for a cancer cell to survive this trip. It's an absolute gauntlet.
See, our bodies have this brilliant security system built right in. Pretty much all of our cells have a self-destruct button. And the idea is if a cell wanders off and ends up where it shouldn't be, say a skin cell floating around in your bloodstream, that button is supposed to get pushed, stopping it from setting up shop in the wrong neighborhood. Now, this self-destruct process has a specific name: ferropoptosis. The ferro part comes from ferrum, that's Latin for iron. The easiest way to think about it is like a controlled cellular rusting. It's this iron-based process that's specifically designed to destroy any cell that's gone rogue. It's basically our body's natural defense against metastasis. Okay, so if ferroptosis is the weapon, our healthy cells obviously need a shield, right? And they've got one. It's a super important protein called GPX4. And under normal circumstances, this is the main shield that protects our cells from that cellular rust. So for any cancer cell to successfully spread, it has to figure out a way around this whole system.
And that right there brings us to a huge scientific mystery, a real head-scratcher that we're going to get into right now, a puzzling survival story.
So here's the exact puzzle that scientists were trying to piece together. When melanoma cells start to travel, one of their very first stops is the lymph node. And based on everything we just talked about, they should die there. It should be a suicide mission. So the question is, why don't they? How do they survive?
I mean, the lymph node is an incredibly harsh place for these cells. The oxygen levels are super low, like only 1 to 3%, and this low oxygen state, it's called hypoxia, is known to seriously weaken that main GPX4 shield. So logically, their main defense is down, these cancer cells should just rust away and die. But they don't. They actually thrive. How in the world is that possible?
This is where the detective work really begins. Let's get into it. The cellular shield switch.
To solve this mystery, the researchers did something so clever. First, they put melanoma cells into mice. Then, they waited and found the very few super tough cells that actually managed to make it to the lymph nodes. They took those cells out and put them into new mice. And they did this over and over again for 9 generations. What they ended up with was a population of what you could call super metastatic cells, cells that were total experts at surviving in the lymph nodes.
And when they studied these expert cells, they found the answer. It turns out cells don't just have one shield against this rusting process, they have 2. There's GPX4, the main shield, that works when everything's normal. But there's also another protein, FSP1, that acts as a backup shield. It can do the same job, but usually it's kind of just sitting on the sidelines.
And this is where it gets really interesting. When the scientists looked at the protein levels, they saw exactly what they figured they'd see for the main shield, GPX4. In a regular tumor, levels are high, right? But in the lymph node tumors, the levels just tank. The main shield is failing.
Apat, and this is the big reveal. Look what happens at the exact same time. The backup shield, FSP1, does the complete opposite. In a regular tumor, it's barely there. But in the lymph node, its levels are through the roof. The cancer cell is pulling a defensive switcheroo.
So, here's the crucial discovery. That hostile, low-oxygen environment in the lymph node is the trigger. It literally forces the cancer cells to drop their main GPX4 shield and go all in on their FSP1 backup just to survive. They adopt on the fly. It's incredible.
And that adaptation, that clever survival trick, it actually reveals a brand new vulnerability. Welcome to what might be the most exciting part, a new Achilles heel.
Okay, this slide, this is the one that changes everything.
The researchers tested a drug designed to specifically break that backup FSP1 shield. Now, when they used it on tumors just under the skin, where there's plenty of oxygen, it basically did nothing. The tumors grew just fine. But when they used that exact same drug on the tumors growing in the low-oxygen lymph node, it was devastating. The tumor growth was almost completely shut down. The cancer's greatest survival strategy just became its fatal weakness.
The researchers themselves said it perfectly in their paper for the journal Nature. They said FSP1 dependency is markedly enhanced within the lymph node environment. What that means is it's not just about the cancer cell, it's about the cancer cell in its specific environment. Context is everything.
So what does this all mean for the future? How can we use this? Well, let's wrap this up by looking at what this means for targeting cancer's weakness.
So let's just recap what we've learned, because it's pretty profound. Cancer cells are masters of adaptation. They literally change their defensive playbook depending on where they are in the body. That unique low-oxygen environment of the lymph node, it forces them to make a switch from the GPX4 shield to the FSP1 shield. And that switch, that very active survival, creates a totally unique vulnerability that we can now target. It proves that if we understand the context, the specific battlefield, we can design incredibly precise attacks.
And that just leaves us with this one final, really powerful question. The lymph node is just one environment in the body. So what other unique environments, like the bone or the brain or the liver, what other hidden weaknesses could they reveal? It feels like cancer's secret survival guide has just been cracked open, and we've only just read the first chapter.